how to determine the pH when you have a weak base, a strong acid, and it is at the equivalence point. Here we go. We've got ammonia weak plus hydrochloric acid. Notice that I write it as H3O plus. You can write it as H plus. Trust me, it's a little bit easier to write it as H3O plus because then you can see the water. Both of these, we are given 25 mils of a 0.016 molar. Where we begin, always, number one, when you have something strong with something weak, you have to do initial final moles. The strong will rip through the weak and we have to see what's left over. So let's begin with our moles. I have 0.025 liters. I just converted milliliters to liters times 0.016 moles per 1 liter. And that's going to give me 4 times 10 to the negative 4 moles. And that's for both the NH3 and the HCl. So for my initial final moles, I'm going to do I and F. We begin with 4 times 10 to the minus 4 moles and 4 times 10 to the minus 4 moles. Now, of course, when this reaction begins, I have no ammonium and the water, that's just a dash because it's a liquid. It is not going to be a part of an equilibrium that we will eventually see. Now, these two, perfect stoichiometric ratio, they will react and both be consumed, 0 and 0. Now, what's produced in the ammonia, be careful on this. 1 mole of ammonia produces 1 mole of ammonium. That means if I consume 4 times 10 to the negative 4 moles, I produce 4 times 10 to the negative 4 moles. You know the mistake students make. They will add those two together. That's not correct. It's not 1 plus 1 equals 2. It's 1 reacts with 1 to produce 1. So there's my 4 times 10 to the minus 4. Now, what grabs me? Because these are 0, I do not have any of the acid or excuse me, I don't have any of this base or acid remaining. It's only the conjugate acid. That means we are at the beautiful equivalence point. The moles of the acid equal the moles of the base. So the only thing that's going to impact the pH is this conjugate acid. That means I have to go to step 2. So here's my step 1, initial final moles. Step 2, I call it the dilution. We need to find the new molarity of what's left over. So I call this the dilution step. We've got to find the total volume. Remember, we added 25 mils and 25 mils. So write it down, 25 plus 25 gives me 50 mils, which is our 0.05 liters. So now we can find the new molarity. I'll simply take this volume right there, or excuse me, these moles, 4 times 10 to the minus 4 moles of the ammonium, and divide it by my new volume, 0.05 liters. And that's going to give us 0.008 molar. Let me double check that. I had done the work. 3, yes, okay, I did my mental math right. Molar of the ammonium. Okay, so that is floating in the solution. That's going to partially react with the water because it is a weak acid. That will determine the pH. So here we come to step 3. It is an ice table. You do the ice table for the conjugate, what's left over. I'll go back to the purple so it's a little bit easier to distinguish this. So we're going to write down the reaction for ammonium in water. NH4 plus the water. Notice here an equilibrium. This is a completion. That strong acid rips through the weak base. Here is a weak acid in water, a weak base. It partially reacts. It goes into equilibrium. And this will produce ammonia plus hydronium. Now I do my ice table. Initial change and equilibrium. Initially, this is the only thing we have in the water right now, is the 0.008 molar, and we have to use molarity in this. That's why I converted this to molarity. Dashes for my water is considered a constant, not a part of our equilibrium expression, 0 and 0. So when this first is produced, I don't have any of the hydronium or the ammonia. It's going to partially react. That's minus X plus X plus X. And then equilibrium, add these together. 0.008 minus X, X, and X. Let's write down the equilibrium expression. This is an acid in the water, so this will be a Ka equals my ammonia plus the hydronium, or excuse me, not plus, be so careful. That is multiplied, that is always multiplied, divided by this, my ammonium. Now you can look up the Ka for ammonium. It is 5.6 times 10 to the negative 10 equals X squared divided by 0.008 minus X. I'm going to double check the, yes, I had that memorized. Wanted to make sure the 5.6 was correct. Okay, so from here, I'm just going to multiply both sides by the 0.008, multiply that by 0.008. And after we do that, I'm going to square root both sides. Let me see if I have this written down. When we take, I just have it to the point that we do the square root. I'm going to take the square root of that side. Notice, oh, this X, because this is 10 to the minus 3, that's 10 to the minus 10, that is considered negligible. So the 0.008 cancels. I can take the square root and notice I get X. There's my X, I took the square root. Take the square root of 0.008 times 5.6 times 10 to the minus 10, and that gives us 2.12 times 10 to the negative 6. What did we just find? Oh, hydronium. Hydronium is X. Hydronium. Okay, beautiful. Now we can find the pH. I simply do pH equals the negative log of the hydronium. So let's plug this in. pH equals the negative log of 2.12 times 10 to the negative 6. And that is going to give us pretty darn close to 5.8, 5.67. 5.67. And that is our pH. I am so proud of you. If you need more support, I have all of this discussed in detail. You can look at the last video that I have posted. It will pop up here. You're welcome to watch more videos or check out my playlist on acid base. Please like and subscribe. So glad that you joined me on Old School Chemistry. I'm really proud of you. Thank you.